Okay, folks, once more into the breach. We're going to finish this chapter and maybe start a little bit of the next chapter. No rest for the weary. Ideally, I will see you on Friday. So, engine design and catalytic converters. So, one way to maximize combustion is by changing the fuel mixture to try to increase the amount of oxygen to make sure it burns completely. Under these lean fuel mixtures, we can have a higher combustion temperature as we can compress oxygen more without risking the premature combustion. Thus, it will increase the fuel efficiency. However, this comes with its own drawbacks. So, more air means we have more nitrogen. More compression means higher temperature. So more nitrogen plus higher temperature means we produce more nitrogen monoxide. So if I don't have enough oxygen, I get incomplete combustion, carbon monoxide, and VOCs. If I have too much oxygen and too much air, I get more NO. So we need a very careful balancing act to maximize our fuel efficiency while minimizing our byproducts. So, as you see on the chart, rich of fueled aero versus lean. That one goes up, the other goes down. If you get a stoichiometric ratio of fuel to fuel to air, you get more NO than you get VOCs. So your computer's going to try to calculate that to try to get the maybe lowest point for each. Maybe right there, for example. Now, current technology uses a three-way catalytic system that will reduce these byproducts. One, our combustion is carried out at near stoichiometric ratio to minimize all of the types of gas. Then our exhaust will interact with two different catalysts. The first one is a rhodium catalyst that will convert our NO using the following two reactions. That two NOs, two carbon monoxides, will form nitrogen and carbon dioxide. And then NO plus hydrogens will form ammonia gas and water. Now you say, well, we've never added hydrogen into the reaction. Well, because combustion is a lot of radical chemistry in itself, hydrogen becomes a byproduct of some of the combustion reactions. And so we produce a little bit of hydrogen that can do this reaction. But either way, we're either forming carbon dioxide and nitrogen or ammonia and water. It all depends. Now, the second catalyst, probably platinum or palladium, sometimes iron oxide or cobalt oxide mixed with chromium oxide, will remove the hydrocarbons and VOCs and the ammonia, so we're not pumping out ammonia out of our tailpipe. So the RH, the VOCs, essentially carbon hydrogen bond, can react with oxygen in these catalysts to produce CO2 and water. The amount of CO2 and the amount of water depends on how big the VOC is. Any carbon monoxide can be oxidized by this process to CO2, and any ammonia can be oxidized to form nitrogen and water. This platinum, usually second catalyst, is probably why people steal your catalytic converters. Platinum is a pretty rare metal. But the net effect reduces our emissions by about 80%. However, this needs a hot system to work. So when your car initially starts, you're dumping a bunch of VOCs and NO out the tailpipe because the car needs to warm up before the catalytic converter actually works. Now, a two-stroke engine is a little bit bigger of a problem. The engine injects fuel air mixture simultaneously, which is then drawn into a chamber as the piston begins to compress. So you can see right there, starting from the dump position. As it strokes up, the gas fuel goes into the chamber and fills that arm. It strokes down to release the exhaust. It has a chance to let the fuel up into the chamber, then it can be dumped as it comes back up. So it's basically, there's some gas in that chamber. As it's stroking down, it's pushing it's constantly putting fuel in as the exhaust is being dumped out. Now, the part of the problem is this: as you can see, there's times when the fuel and air is mixed with the exhaust gas. So there's some of the fuel and air has a chance to escape with the exhaust gas at the same time. This actually results in a much higher amount of VOCs escaping at the same time. And in order to make it work, it often uses a heavier hydrocarbon mix. That heavier hydrocarbon, so bigger fuel chains, means it's less efficiently oxidized, so it doesn't get completely burned. But it's a lot easier to make. It's a lot easier engine to make. You can make them a lot smaller too. So take that as you will. Now, in a marine boat motors, the emissions, it's similar to vehicles in our tools, but part of the problem is instead of releasing it to the atmosphere, it dumps it directly into the water supply. So it doesn't go into the air, it goes into the water. So, but both the two-stroke and the four-stroke have the same power output, so emissions can be compared directly. So we can compare energy, but we can't necessarily compare we can compare energy, so we can compare the fuel to some extent. So like two-stroke produces more carbon monoxide, but far less NOx, but way higher VOC. So like less NO, but higher partially oxidized carbon and higher VOCs. Now, while catalysts can be used to reduce the emissions of two-stroke, the exhaust often needs to be cooled down first. So that's an issue. Now, the next table actually compares 125cc high-powered motorcycles. Compare it from fresh from production with an optimized carburetor and output gas scavenging, and then with a catalyst, and the final thing. So with the catalytic converter, the final is the strict Swiss standards of what is allowed. So if you look at straight from the factory, it's already under the carbon monoxide allowed. It's already around below the NOx, but the VOCs are way higher. They're 3 when they it's almost 17 when they need to be 3. So we optimize the engine, which drops the carbon monoxide, drops the VOCs, but not quite enough, but increases the NOx. Well, if we take that optimized engine and then add a catalyst, we see a greater drop in NO, a small drop in NOx, but that big drop in our VOCs. So it's suddenly, with a catalytic converter, that's what keep it under that Swiss standards. Now, the diesel engines, they have a slightly different system as well, but it kind of looks like our Otto cycle. They're commonly used for many much larger vehicles. Now, because of their nature, we can have a much higher compression ratio. We can compress our gases a lot higher and have them burn hotter, and so we get much greater fuel efficiency. So diesel engines will always get much greater mileage. Sure, diesel costs more at the pump, but you get much greater mileage for it. So we can get larger pressures, so higher temps, and so it will allow the fuel to ignite without a spark plug. There will be no spark plug necessary. But that also adds problems. They don't do so well in the cold. When the engine is cold, it's really hard to get started because you have to compress this cold air to a really high temperature to auto-combust the fuel. And the fuel, because it's bigger, is also sludgier. It's more viscous, and so it doesn't move as well. So you often have to warm up the engine by external means to get it to kind of start. But once it goes, it goes better. But that's because when we initially compress the gas, we are only compressing pure air. So when we're in position E, we have no gas. We let all this gas in. So in the intake, we're then, so starting at the end, we're compressing it down. So there's almost no space. We, at the point where we're at the top of the compression, we're injecting our fuel. And because you're injecting the fuel into this high temperature, highly compressed gas, it auto ignites and you get the power stroke. So it combusts from B to C and you get the power stroke down to D. And then we allow the exhaust gas to everything to flow back out to get all the way to E, and we're ready for the intake again. So because we have this compression ratio of 15:1, we can get a higher temperature of like 500 degrees Celsius. And so we don't need as high grade fuel. We get higher boiling fuel and burns with higher efficiency, and so all around it's a better fuel, except when you're in the cold. But due to when the fuel becomes added, combustion is often incomplete, though, because we're adding the fuel at the very end. It doesn't always get a chance to burn completely. It's not already in there. Diesel exhaust contains a lot of unburned carbon particles, soot, and a lot of soluble organic fraction. So the soluble organic fraction is unburned, partially burned fuel that can form a liquid aerosol and other components that then become sorbed onto soot particles. So we get these liquids that kind of encapsulate and form onto the solid soot. But we still have less gaseous exhaust compared to the normal four-stroke. So we get more solid and aerosol-based waste, but less gaseous waste. And also the nature of the diesel fuel, there's a lot more sulfur, higher sulfur content in the diesel fuel, and so we often get more sulfates and sulfur dioxides from there, because diesel can range between 0.1 to 0.3% by sulfur. And because we have a higher temperature, we get a higher amount of NOx. Now, the soot can be removed by filters and traps, but these traps need to be cleaned because you're absorbing the soot onto them. It's like you're vacuuming it out. So every now and then you got to change the vacuum bag. You got to empty that trap. You burn off the soot. Their better option is an oxidative catalyst like platinum or palladium on some sort of high surface area substrate. But because of the sulfate can poison these catalysts, so we have to account for that. So we alumina won't work because alumina will react with the sulfate. So we need to find something else to bind the platinum or palladium to get this to work. Now looking at biodiesel real quick. So biodiesel is fuels that we're essentially converting fats into diesel fuel. So it's a recent fuel design innovation allows for diesel engines to use fuels derived from fats and oils. We can use soybean oil, various oil seed product producing trees and shrubs that can be grown in wastelands and scrublands. Basically, places we cannot easily grow crops. I mean, just looking at along the sides of roads or in tree. I mean, it's basically we can grow this crappy trees that can grow anywhere and then convert this into fuel. These waste fats and oils from restaurants and other sources can be used as fuels as well. The basic idea is these fats look like this. We have this glycerol acid component and this carbon component. When we use a base catalyzed deesterification, and what happens is these triglycerides form the biodiesel. So the biodiesel is essentially a long chain esters. Long chain esters. Ester is a carbon-oxygen carbon bond with a carbonyl, the carbon double bond coming off of that. That's what we have here. These are esters right here, but it's a triester. This is the basic triester that is in fats, triglyceride. We're basically breaking this triester into single esters that can be used as the fuel. Now, so the carbon chains can be anywhere between 14 and 18 carbons. So, and we're removing this glycerol, which is what that is at that point. Now, some advantages is that it can be produced from renewable resources, even waste products. People will pay you to take their oil off their hand, and then you get fuel from it. It's great. Now, the oxygen content from the ester also increases the combustion completion, lowering the VOCs from the unburned hydrocarbons. And because the oils are not taken from the ground and contain little sulfur, we don't produce as much sulfur waste. So biodiesel is most commonly used in commercial vehicles like buses. It be used as pure biodiesel or in a 20 to 80 ratio. Now, biodiesel 100 sees a 48% reduction of carbon monoxide, 47% reduction in particulates, 100% reduction in sulfates, and a 50% reduction of ozone potential for only a minor increase of 10% of the NOx produced. However, B20 sees a 12% carbon monoxide, a 12% soot, 20% reduction in sulfates, 10% reduction in ozone potential, but only sees a 2% increase in NOx from comparing of using full diesel. Now, ozone production. So in the complete mixture of emission gases, many gases have more potential to cause trouble. Some gases have more potential to cause troubles than others. So remember, secondary reactions will form these tropospheric ozone. This is a byproduct of a sequence of reactions that result in hydrocarbon oxidation. And in order to reduce ozone, we should try to reduce the nitric oxide and the hydrocarbons themselves. So if we can stop these initial reactions before they start, we won't get to the point of ozone. Now, while it's ideal to reduce both NOx and VOCs, it's not. You have to choose. It may be easier to consider which of the two should be a limiting reactant, because you can't remove all of them. So what can we remove? How? So consider the plot of this ozone isoplenth. This is a contour plot at a constant concentration. We look at these 3 points, A, B, and C. So different amounts of ratios of VOCs to NOx. So NOx is on the y-axis, VOC is on the x-axis, and these lines are the amount of ozone that would be formed. So if we're at point A, the VOC of 1.8 ppm, and NOx of about 0.8 ppm, the ozone would produce about 0.24 ppm. If we were to reduce the VOCs to point B, to 1 ppm, without changing the NOx by much, you would have no change in the ozone. So, yes, in the long run, yes, you're cleaning up the air, but you still get the same amount of ozone. However, if we were to reduce to point C, change the NO to 0.02, and leave the VOCs at 1.8, the amount of ozone produced drops to 0.08 because NOx is limiting. Looking at this isoplenth, if NOx is limiting, reducing the limiting reactant reduces how much product you can get. If NOx was limiting, going from A to B, removing some of the excess reactant didn't really affect our rate. Didn't really affect how much would form. So, however, looking at this, it's often better to try to make the VOCs to be limiting, as they pose additional health hazards. So, we want to be on the top half of this equation, if possible. But so just that's on to think about. So let's see how we're doing on time. We are 22 minutes. I'm going to introduce just the bit of the next chapter, which is the chapter on acid rain. Try to get it to a nice even 30 minutes or so. So tropospheric precipitation. So in this chapter, we will look at the composition of natural precipitation and how it is affected by natural and anthropogenic influences. We're going to look at the atmospheric methods of production and removal of nitric and sulfuric acids. We're going to take a global look at the sources and sinks of nitrogen and sulfur compounds, and some technology we can use in chemistry to control the NOx and SO2 compounds. Now, this is one of the most publicly widespread environmental issues, acid rain. It's well known, we can directly see the effects. Everyone can argue one way or another, oh yeah, we're seeing global warming. No, we're not seeing global warming. But hard to ignore acid rain when it's like, oh, my statues are dissolving. Oh, look at the damage to these structures. Look at all this rust and this is falling apart. The rain, you can directly tell, yep, that's acid. That's good, not good. Emissions near energy or smelting industries can lead to precipitations of pH of 4 or less. Remember, pH 7. pH 7 is perfectly neutral, neither acidic nor basic. We're going to talk about pH 6 and even sometimes pH 5 is somewhat normal. And this is a logarithmic scale. So from neutral, this means pH 4 or less. That is more than 1,000 times more concentrated than neutral. So this leads to acidification of lakes, which will affect growth of forests and cause damage to stone buildings. This was a big problem in the 60s and 70s. We've led to a lot of improvement in some of the previous areas. But the problem has shifted to other regions of the world. So even though we had the problem in America, we fixed said problem, America and Europe, now other developing nations are having the same issues. they're coming through the same growth problems that we did. But so the focus of this chapter is actually just rain in general, not just acid rain. This is called wet deposition. So depositing of chemicals through wetness. Dry deposition, when we look at, it will be next chapter when we look at aerosols and other things, that dust particles and whatnot. So the composition of rain. Now, rain contains a wide variety of naturally occurring ionic salts and dissolved gases. Rain is not pure. It's not pure water. It can never be pure water. Gases will be dissolved partially with regards to Henry's Law, which Gen Chem 2 learned. Whether they learned it well, it's to be seen. But it's the solubility in molarity is equal to a constant, Henry's constant, for that gas times the pressure of that gas. So higher pressure means higher solubility. However, further reactions in water with water will increase solubility. So CO2 should be low. But because CO2 can react with water to form carbonic acid, it increases the solubility of CO2 versus oxygen and nitrogen. Now, CO2 dissolved in water is largely why rainwater is naturally acidic, about a pH of 5.7. So remember, 7 is perfectly neutral. So 5.7 is normal. So slightly acidic, a little bit over 10 times more acidic than neutral. So maybe 20, 30 times more acidic than from a zero-sum game. Now, there are also natural sources of acids, such as organic acids and sulfur compounds that are produced by microbial processes on living or dead biomass. Dust will contain calcium carbonates that are mildly alkaline, basic, and that will increase the pH. If you combine all the factors of all these things, unpolluted rain can range somewhere between 5.5 to pH 8 or above. So there's a wide range, but notice 7 is neutral, so 5.5 is a little on the acidic side, but not too bad. 8 is a little bit on the basic side, but not too bad. It all depends on where we're at. Now, other ions that form in the rain will depend heavily on the where the rainfall occurs. If you're near an ocean, you're going to have a much higher concentration of sodium and chloride, and to a lesser extent, potassium, magnesium, calcium, and sulfate. Big salts that are present in the ocean. Similarly, some sodium chloride or calcium chloride can come from, very apropos, the salt used to melt the ice and snow on the highways during the wintertime. Like right now, we're cleaning our sidewalks, we're dumping some of the salt on here to help reduce the freezing point of the ice so it melts more easily. So that will dissolve into the water. As the water evaporates, it takes small amounts of the salt with it. If you're in an area that's rich in limestone, it's going to produce some dust that the water can dissolve. And this is going to increase the amount of calcium and magnesium. If you have a bunch of farm areas, so a lot of biological processes can release ammonia that can form ammonium ions that can dissolve in water. So plants and animals, you got some waste, you got some poop, you got some plants doing its normal processes, you're going to get some ammonia. You also have a high amount of fertilizer, you can get some ammonium. But so here's just looking at some of these situations. I took the I looked up where these locations were at so we could better tell these things. So, urban area, Guiyang, in People's Republic of China. And I highlighted some of the ones that are higher than average and lower than average. The concentration of hydrogen, very high, but the pH is very low. It's very acidic. We have a lot of acid rain. They didn't measure any chlorine. It's a decent amount of nitrate, but not the highest. The big concentration that we see is sulfate. So we get some sulfuric acid rain. It's a little high on the calcium, but not necessarily compared to some of the other ones. Ammonium, a little high, but not too bad. Looking at Norway, the next one. This is near the southern tip of Norway, near the sea. It's specifically there, Berkines of that little quadrant. It's not that acidic. It's a little acidic, but not too bad. We have a little high on chloride, but not the highest. Pretty high relative to the other values of sulfate. Low on calcium, a little high on magnesium, a little high on sodium. So we might get some sea spray, but not too bad. Look at Catherine, Australia. That's definitely near the ocean. It's not very acidic. Well, at least it's one of the least acidic ones. But we see a relative concentration of chloride is not that high, actually. That was probably the most average of all of our values, a lot lower than everything else. But it's kind of maybe urban, a bit more rural. Pune, India. Surprisingly, very high nitrates, very high calcium, very high potassium, very low sulfates. And it's actually the least acidic. I think that has to do with its and very high sodium, but that might be in relation to everything else. Looking at things out of whack, but that may be due to the clay-based soils there. We have greater amounts of calcium and potassium and nitrate. And St. George's and Bermuda, definitely near the ocean, though surprisingly we have a lot lower sulfate and calcium and potassium with relation to your other things like sodium and chloride. So, since sodium, potassium, magnesium, calcium, and chlorine are common and naturally occurring and benign in the micromolar concentrations, they're usually of minor significance. It's the nitrogen and sulfur species that we need to worry about, largely. They will contribute to the increasing acidity of the rain. Now, the sources can come from a wide variety of natural and anthropogenic. So we can get NOx, obviously, from burning stuff. That our whole last chapter we looked at NOx. It can be high in urban and low in remote, and it can last a long time or very short time depending on the heat. But we can also get ammonia that can form that, and that can come from fertilizers and natural processes. Sulfur, SO2, has a little bit of a range, but it can come from diesel fuel, remember, and some biomass, but it also can come from oil smelting, so turning the ore like coppers and irons into and usable metals. We can get hydrogen sulfide. This can come from submerged soils and wetlands. We're going to have a whole chapter devoted to looking at these processes by which soils are going to the water in the soil is going to be reducing and produce these hydrogen sulfides. Carbon disulfide, also submerged soils and wetlands. These are natural sources. We can't control these. Dimethyl sulfide coming from the oceans. Can't really control these. Carbon sulfide, oceans and soils. Methyl mercaptan, oceans and soils. Dimethyl disulfide, can't really control these guys too much. It's coming from natural processes. So what we can control is the amount that's coming from our fossil fuels and biomass. So, let's see. I think I'm going to try to stop there. We'll stop there, and we'll pick up on acid rain on Friday.